NASA just recorded another update on 3I/Atlas today, and the word they used inside the report says everything. Unsettled. Not stable, not calming, not predictable. Unsettled. If you've been following this interstellar visitor with me and you don't want to miss what happens if it keeps refusing to calm down, make sure you're subscribed, drop a like, and stay with me till the end, because today's update quietly confirms that 3I/Atlas is still in the middle of something, not at the end of it. Here's what NASA saw this time. The first red flag didn't come from a beautiful image. It came from the part nobody outside the mission ever reads, the fit quality. Every day, observatories and spacecraft send in new position measurements, tiny dots on the sky that tell you where 3I/Atlas actually was at specific times. You feed those into an orbit solver and ask, does yesterday's solution still work? Today, the answer was no, in a very specific way. When they used yesterday's parameters, same non-gravitational forces, same spin-linked outgassing model, the predicted positions and the real positions didn't just miss by a little, they missed in a pattern. All the new points sat slightly off to one side of the predicted track, like the comet had quietly leaned away from the path they'd just finished refining. That's not random noise, that's behavior. To fix it, they had to tweak the non-gravitational acceleration again, the tiny engine effect from gas jets pushing on the nucleus. The updated fit wants the push to be tilted in a new direction and to stay stronger than the fading comet models allow. In other words, the trajectory is unsettled because the forces driving it are unsettled. While the orbit team was wrestling with that, the imaging team was doing what they always do, stacking and sharpening the latest deep exposures to see how the coma and tail have changed. And the pictures tell the same story in a different language. In last week's stacks, the inner coma looked stretched but coherent. One main bar of brightness, a clear preferred axis, and a tail that curved in a way you could almost get used to. In today's stacks, that inner structure has twisted again. The brightest part of the coma is no longer aligned with the old bar. It's rotated, like the spine inside the glow has been grabbed and turned a few degrees. One side of the inner coma has thickened, the other has thinned and grown ragged. Even farther out, the tail shows a faint kink, a subtle bend that wasn't there before, as if the stream of dust has begun to track a new direction of thrust coming off the nucleus. None of this screams catastrophic event. All of it quietly whispers, nothing here is settled. Then there's the rotation. To understand how 3I/Atlas is spinning, NASA's teams track how its brightness rises and falls over hours. A stable rotator gives you a clean, repeating light curve, same peak height, same timing, cycle after cycle. That is not what today's light curve looks like. When they folded the newest photometry over last week's rotation period, the peaks didn't match up. Some peaked a little higher, some a little lower. The timing shifted just enough that a single period couldn't make the whole pattern line up. To get a decent fit, they had to allow the rotation period itself to drift again and add a small change in amplitude from one rotation to the next. Translated, the comet's spin is not just speeding up or slowing down smoothly, it's wobbling. Sometimes more area faces the sun, sometimes less. Sometimes the most active regions line up just right, other times they're half in shadow. The result is a brightness pattern that refuses to settle into one simple rhythm. So, line up the three main pieces of today's data. The orbit solution needs yet another adjustment to the outgassing force. The coma and tail geometry have twisted with new asymmetry. The rotation signature is drifting and irregular, not locked in. That's the observational meaning of 3I/Atlas unsettled. The obvious question is, what's actually going on inside this thing? One picture that fits the data is this. The nucleus of 3I/Atlas is being pulled in three directions at once. Thermally, it's still adjusting to the heat it absorbed near the sun. The outer layers already blew off their easiest ices. Now, deeper, more stubborn pockets are catching up at different depths along different fracture networks. Dynamically, its spin state is being pushed around by those jets. Every vent that's even a little off-center applies a torque over thousands of rotations. Those tiny torques add up, tilting the spin axis and changing which regions get cooked in the next cycle. Structurally, all of that is happening inside a body that was never meant to be a rigid rock. It's a porous, ancient, cracked mass from another solar system, trying to redistribute stress fast enough to keep itself in one piece. On some days, those three influences line up just enough to make it look like 3I/Atlas is calming down. The brightness drops a little, the tail looks cleaner, the orbit solution holds for more than one iteration. Then a deeper pocket vents, a new crack connects to the surface, where the spin wobbles a few degrees, and everything shifts again. That's where we are today, not in the middle of a dramatic explosion, not in the comfort of a quiet fade, right in between, unsettled. There's another more subtle clue buried in the latest spectra, the breakdown of the comet's light by wavelength. Compared to earlier in the encounter, the ratio of gas emission to dust reflection near the nucleus has shifted again. Certain lines associated with deeper volatiles are still noticeable. The inner region shows a slightly different color balance than the outer halo. That suggests new material from inside the nucleus is still being tapped, not just recycling the same surface layer over and over. Every time that happens, you're not just adding gas to the coma, you're forcing the interior to rearrange. Pressure pockets empty, voids form, overlying crust collapses or sags, and stress lines move. If those new stress patterns found a new equilibrium, the data would eventually reflect that. Stable spin, stable jets, stable non-gravitational term. The fact that everything in today's update needed another small correction is NASA's way of saying that equilibrium hasn't been reached. So, where does this go? In the best-case scenario, 3I/Atlas is currently in the last noisy phase of its evolution. The remaining packets vent, the wobble damps out, the jets weaken, and it leaves our solar system as a scarred, slightly elongated but intact interstellar comet. In the more worrying scenario, the unsettled behavior is a sign that the internal stress is still climbing, that each new vent and spin tweak is pushing the structure closer to its limits. Comets from our own system have taken both paths. Some survived their chaotic perihelion and stabilized. Others stayed unsettled until one update wasn't just that the data shifted, it was that the nucleus is gone. Right now, 3I/Atlas is still officially one object. No confirmed fragments, no clear debris stream, just a lot of motion under the hood. But today's log is the kind of quiet turning point that matters. The numbers aren't calming, the shapes aren't calming, the spin isn't calming. They're all still evolving, and not in a simple direction.
Think about what this means for a moment. We're watching an object from beyond our solar system, something that's traveled through interstellar space for who knows how long, now going through changes we've never witnessed before. This isn't like watching a familiar comet we've tracked for decades. This is genuinely new territory. The way 3I/Atlas is behaving tells us something profound about the nature of interstellar objects. They don't play by the same rules as our homegrown comets. The composition might be different, the structure could be radically unlike anything we've studied up close, and the way it responds to our sun's heat is giving us clues about conditions in whatever distant stellar system it came from. Every measurement, every slight deviation, every unexpected twist in the tail is a data point we've never had access to before. Scientists are literally writing the textbook on interstellar comets as this unfolds. The models they're building right now will inform how we understand these visitors for generations to come. But here's what makes this particularly fascinating. The unsettled nature of 3I/Atlas isn't just a quirk or an inconvenience for the researchers trying to track it. It's information. Each wobble, each shift in outgassing, each adjustment needed to the trajectory calculations is telling us about the internal structure and composition of this object in ways we couldn't learn if it was behaving predictably. When you see that the rotation period keeps changing, that's not just messy data. That's the comet telling you about its mass distribution, about where the heavy parts are versus the light parts, about how irregular its shape must be. A perfectly symmetrical sphere wouldn't wobble like this, but 3I/Atlas clearly isn't anything close to symmetrical. When the jets keep firing in unexpected patterns, that's revealing the geology, if you can call it that, of an interstellar object. It means there are pockets of volatile material at different depths. It means the internal structure has layers or veins of different compositions. It means this thing has a history written into its physical makeup, and that history is from somewhere completely different than here. The spectral data is particularly intriguing. Those deeper volatiles they're detecting, the ones that are still showing up even though the comet has moved away from its closest approach to the sun, those are materials that were buried, protected, preserved from whatever this comet has been through in its long journey between the stars. Think about what had to happen for those materials to still be there. This object avoided being completely stripped by whatever star it originally formed around. It survived ejection from its home system, possibly in some violent event. It traveled through the radiation-filled environment of interstellar space without being completely sterilized, and now it's releasing these preserved samples right where we can study them. Every gas molecule escaping from 3I/Atlas right now contains atoms that were last part of a forming planetary system around a different star. The carbon, the nitrogen, the oxygen, whatever complex molecules might be hiding in that mix, they all tell a story about chemistry that happened light years away. And the structural response we're seeing, this refusal to settle down, is probably telling us that 3I/Atlas is more fragile than it looks. Comets from our solar system can be pretty tough. They've been through many passes around the sun. They've developed protective crusts. They've lost their most volatile components long ago. But 3I/Atlas is a first-timer in our solar system. Whatever protective mechanisms it had from its original environment, they might not be well suited to our sun's particular flavor of radiation and heat. It's like watching someone from a cold climate suddenly dropped into a desert. The adaptation is happening in real time, and it's messy. The fact that NASA keeps having to revise their models isn't a failure of their science. It's actually a success of their observation methods. They're catching changes fast enough to see them as they happen. If they were only checking in once a month, they might miss these transitions entirely. But with daily updates, with continuous monitoring, they're getting to see the evolution play out step by step. This is why the word unsettled is so perfectly chosen. It's not catastrophic, it's not stable, it's in flux, it's transitioning. And transitions are often where the most interesting science happens, where you learn the most about how systems work under stress. Now, imagine you're one of the scientists watching this data come in every day. You spent your career studying comets, maybe even interstellar objects in theory, and now you've got live data from a real interstellar visitor going through its closest solar approach. Every morning you check the latest observations, and every morning something has shifted again. That would be simultaneously thrilling and nerve-wracking. Thrilling because you're seeing things no one has ever seen before. Nerve-wracking because you genuinely don't know if tomorrow's update will show continued changes or something more dramatic. The comparison to comets that have broken apart isn't alarmist, it's just realistic. We know from decades of comet observation that there's a line between stressed but holding together and stressed past the breaking point. We've seen comets cross that line, sometimes slowly, fragmenting piece by piece, sometimes suddenly, just gone one day. 3I/Atlas hasn't crossed that line, but the continued unsettled behavior means it's operating in a regime where that line exists and is potentially reachable. The question is whether the internal forces causing all this activity will exhaust themselves first, or whether they'll build to a point where the structural integrity fails. And here's the thing about predicting which way it goes. We don't have enough data yet. Not enough examples of interstellar comets under solar stress, not enough understanding of what this particular object is made of deep down, not enough knowledge of its thermal history or structural weak points. So we watch, we measure, we model, and we wait to see what happens next. The beauty of modern astronomy is that we can watch this unfold in near real time. Previous generations of astronomers might have gotten a few observations spread over weeks or months. Now, we get daily updates. We can see the process, not just the before and after snapshots. Every piece of data going into those NASA reports is helping build a more complete picture. The positional measurements constrain the forces. The brightness variations constrain the rotation and surface properties. The spectral data constrains the composition. And when you put all of those constraints together, you start to narrow down what's actually possible. Right now, what's possible is still a pretty wide range, from gradual stabilization to potential fragmentation, with a lot of intermediate scenarios in between. But each day of new data narrows that range a little more. Each revision to the models rules out some possibilities and strengthens others. This is science in action, not the clean, finished product you see in textbooks, but the messy, uncertain, exciting process of trying to understand something genuinely new. So, if you want to see whether the next NASA entry finally says 3I/Atlas is stabilizing, or whether it says the unsettled phase just escalated again, make sure you're subscribed, stay tuned, and as always, stay curious. And I'll see you in the next.